Okay, well, welcome back to the View Dependent podcast, where we are speaking to leaders in the world of hyperreal 3D reconstruction methods like radiance fields, which include both neural radiance fields as well as Gaussian splatting. So today, our guest is Wieland Morgenstern from Fraunhofer. We're very, very excited to have him on the show today. So his work has really done a tremendous job in terms of compressing these Gaussian splatting models, which originally were in the form of multiple gigabytes, and the amount of compression that Wieland will talk about has just been shocking. So we're very, very excited to have you on the show today.
Yeah, also welcome from my side. I'm really excited to have you here because we haven't had the topic compression before on our show, and I'm happy to know more about your work and also how you get the huge files down from several gigabytes to megabytes.
Hi, guys, thanks for having me. Maybe I can start by telling a bit about myself. I've been involved in this Gaussian splitting compression for the last year or so, but I've been interested in the whole 3D reconstruction world for a much longer time, I'd say. I studied at a tiny university in Germany called the Technical University of Ilmenau. It's hidden somewhere away in the Thuringian forest in the middle of Germany. It's a small university, but it's great there. And I studied computer engineering, and towards the end of my studies moved towards computer vision and robotics, and this field has kept me there since then. After studying, I was thinking to leave academia and join the startup working on panoramic video stitching, so putting all together lots of cameras and then creating 360 panoramas out of them that you can then stream to VR glasses and so on. That was a fun time. I did that engineering there for maybe 4 years or so in France.
Did you do the software part or the hardware part as well?
Actually, it was both. So the startup started as a software startup where you would have all these GoPros. You would have like a set of 6 GoPros in a 3D printed encasing, and you would copy all the GoPro files that you recorded to your computer, and then you would run our software Video Stitch Studio to stitch together your GoPro files. And then we were like, okay, this is really tricky to handle the cameras like that and to handle the files. We want to do that live, and developed a live software. So from the like post-processing, it became a live software. And then, but still you had to do all the cabling stuff, and you had 6 cables for 6 cameras or even more cameras. That was quite annoying. And we were like, okay, we really want a single camera. And there wasn't anything on the market at that time. And so we started developing actually a hardware camera.
Okay, so how many cameras did you use or end up using in the end?
In the hardware camera, it was 4. So
4, okay.
Yeah. The idea was to get them as close together as possible, because the closer the sensors are together, the less artifacts you have in the overlapping areas where you need to do the stitching. So we came up with this clever solution where like you had 2 cameras on top meeting there and 2 on the bottom, and they were like interlocked with each other, so really close together. And so you got a really nice quality out of that 4K 360 video that could be live streamed.
And so then how did you become aware of then radiance field based technologies? Like, was it through NERF? Was it really crossing your path most with like Gaussian splatting or a different method?
So that was before all the kind of NERF stuff. So that was just panoramic imaging, and I left them 2018 and started working at Fraunhofer IHI, where I'm currently as a researcher, and started a project working on 3D reconstruction that was about people going together to some like larger field and recording a larger scene together with cell phones, a 3D scene. So people would have like mobiles that would contact each other, and they would build like a church or something in a couple of minutes by cooperating there. And this was before all the NERF kind of stuff. So when the NERF paper came out like 2 years later, I was really excited for that kind of field, and I was excited to get into that. But I had moved on to working on virtual humans by that time, so avatars. And the NERF was too kind of slow to do that in the beginning. So if you remember, right, the rendering a single image from a NeRF in the beginning took like 30 minutes, I think, for the first paper. And we were like, okay, if you want to do a live avatar, we can do that. So I was excited about that technology, but we couldn't immediately use it for our work. Our avatars, our virtual humans, are recorded in a volumetric video studio that we have at the Institute. And so, yeah, for me to start diving into that topic, it needed at least instant NGP, the NVIDIA work with the hash tables that finally made it possible so that you could render the stuff in real time. And so this is when we started looking into it and saying, okay, our human avatars, which we previously built with like meshes and text meshes, now we can look into these radiance fields to get started with that. And yeah.
So you ended up applying radiance fields for the avatars. And by the way, what is the volumetric studio? Because you mentioned it.
Yeah, I brought a clip on that. So for the volumetric studio, so it's a technology. Yeah, this one developed at our institute at HHI, where you have 32 cameras like in a circle around the actor, like really high def cameras, and you will put the actor or two actors in the middle, and then you will do the dynamic reconstruction of the actors of this studio. So yeah, that's what sometimes is called volumetric video, or out of the perspective of radiance fields, you might call it now dynamic 3D GS, or some people call it 4D GS or something like that, right? The dynamic scenes that you can record of people there. And that's quite exciting technology. At HHI, we have a studio like that, and we created they created a startup before I arrived there called Volucap, that is now in the film studios in Potsdam-Babelsberg, my favorite famous film studios there. And it's always fun for me going there. And like for this project here, it was an EU project about avatars in museums. We hired these actors, and then went to the studio in Potsdam-Babelsberg and did the recording there, having them act out like different weird body poses to be able to create a full dynamic avatar. And it's a great environment to be there.
But this is still based on meshes, right? Because you can see the mesh in the video. And
I mean, the studio is a studio. It just has cameras, right, putting out images. So the video I showed is from like the earlier, like the traditional standard process. There's not that many of these studios around in the world, maybe a handful, like half a dozen, that really do this like Hollywood quality kind of recording. And the original process used to be to do textured meshes, but that involves a lot of steps to get there, and it involves a lot of the same things that you will have for Gaussian splatting and radiance fields, like the camera calibration and color calibration. But then you get a point cloud, right? But for your radiance field, you don't need to do the like Poisson meshing and texturing, and need to deal with all these kind of artifacts that you get with mesh. And, so I think these studios also will move to radiance field technology probably in the future.
Along those lines, when you first saw 3D Gaussian Splatting come out, like what kind of led you then to start working within that representation, and then also begin investigating the compression?
I've asked myself that, and it's a kind of tricky thing to pinpoint that. I think I've been interested in for a long time in the kind of remapping like three-dimensional data to other places. For example, with the like video stitching, the panoramic views, you have the problem, or you have the issue. Your cameras are recording around, and if you put them on put your world on a cylinder, you can just like cut your cylinder at one place and you can roll it flat, and that works well. But then you don't get the north and south pole, the like zenith and nadir. They are kind of missing in your world. So what you usually do is you project your stuff to a sphere, so it's on a globe. But then there's this interesting problem that you try to unfold your globe, and it doesn't actually fold flat. It's not like possible to like cut your globe in one place and have it completely flat. You will get creases. or you have to do more cuts. It's an interesting problem. You do in like this kind of panoramic videos, you do the equirectangular projection that you may know. Also, that's a bit looking like the world map, where you maybe know that like countries far up in the north will be much larger on the world map than they will be in real time, and you get these weird like distortions, and you can't actually flatten it. And so this was interesting to me in the kind of panoramic side, and so has been in the back of my mind for some time. And so when NeRFs came around, I was like, okay, this is an interesting new approach. You have the NeRFs are like completely new way of thinking about this world. Like, how does the world around us exist? So it's okay, it's just a 5D function where you say, okay, we just have this network and it's a general function approximator, and we just pretend the world around us is a function. We ask, what is the color at this place and this direction? And this was something really interesting, that this network learns this function and learns it in a really compact way. And so when Insert NGP came around, I was talking to a colleague who was mapping this to 2D images, and this was an interesting approach. And then I was talking to the compression people in our institute also, who were interested in doing NeRF compression. And that's the time when Gaussian Splatting came out, and I revisited this idea of mapping this like higher dimensional world into a flat space. And we will get to why that's interesting in a bit, I think. That's when I started looking at that more closely. And I think you had this video there starting up with, I looked at some of the early experiments that I started doing with it. So the idea was, okay, I want to kind of map this 3D Gaussian splatting scene into a flat space that can be recorded as an image. So that's the general idea. We take the 3D data and we map it into a 2D image that we can encode. You will see like the rendering of the truck scene of Gaussian splatting on the left. And then in the right, you will see this kind of representation that reorders the Gaussians into these 2D images. And so the one window says like XYZ, so that's the coordinates. And the other window says RGB, so that's the colors. Did some clustering of the Gaussians. So you can do a clustering of the Gaussians and see which Gaussians like belong together in the same space and which have similar colors. And then you can reorganize them into these clusters and put them together.
So how do you exactly the mapping? Because I think this is like one of the core ideas of your approach, that you are putting like every parameter of the Gaussians, and there are a lot, I think 59 or so. You put every parameter on a separate grid, right?
So that's a good point. So you can you imagine as you said, the Gaussian has like 59 parameters or attributes. And usually you just have a really long list of them. You have like 1 million of them, and they are just a long list. And the order of them doesn't actually matter, because you just give them to the renderer, and they have their position and their color encoded in these attributes. So you can like reshuffle them any way you want. And so what you can also do is you can, you would say maybe reshape them into this kind of 2D grid. And so it's a bit weird saying it's a 2D grid. So it's a grid in 2D where you have organized your 1 million Gaussians into, let's say, 1,000 by 1,000. And then there's like 59 layers of that going on. And if you access one of these 1,000 by 1,000 with all its 59 attributes, it's like one Gaussian again that you can render. And you can shuffle them around again, but you need to always take the 59 attributes at the same time. So you need to like cut through all the layers at the same time. You cannot have different orders in the different layers. Otherwise, you will have different colors matched to a Gaussian where they don't belong, for example.
So to put it differently, you have 59 layers, and there are the Gaussians mapped to. And if you sort, you have a stable sort. So like every layer sorted at the same time in the same order. Or put it very differently, you could just stack the layers in one array and shoot a ray through one of the grids, right? And you would always hit the same Gaussians, even if you saw it, right?
Yeah. I think that's one way of putting it. Maybe it will also get a little more clearer with upcoming videos. It's always, I think, hard to wrap your head around this at the first try. Yeah, for example, this is a good one of the that I did recently to show this kind of thing. So in one place we have the Lego thing in 3D Gaussian splatting, fully trained, and then you can maybe look at different parts. Look at, for example, at the red Gaussians.
Right.
Yeah, so they are supposed to stick together in 3D, and they are supposed to get close together in 2D as well.
With some sort like UV unwrapping, it looks very similar.
I think there are parallels for this. So yeah, right. What you do in like texturing, where you also want to place things that are close together on the surface of a mesh, you want to place them closer together also somewhere in the UV map.
But if you unfold the RGBs currently, it's just, let's pretend it's RGBs. So here in this example, it would depend on an amount of pixels, right? So you would just reshuffle the pixels. But then in your approach, it depends totally on the number of Gaussians, right?
Yeah. Right. And that if you change the number of Gaussians, you change the number of your grid. And this was one of the like tricky parts in these early experiments. Maybe we can actually you see that grid growing if you go back to the video, like the first experiment video. What you can see over time is that this grid is actually growing over the training time. So that's the densification and pruning of the Gaussian splatting, if you're familiar with the algorithm, right? Where they say, okay, these scenes are under-reconstructed or over-reconstructed. So if the video is playing, you would see on the right that these grids move in size. So you start rather small because you have just a few Gaussians, and then the algorithm would do the densification and add more Gaussians where they are needed because it's under-reconstructed, or remove some where there's too many Gaussians and you don't really need them. And this will reshuffle your grid all the time because this algorithm doesn't care how you ordered your Gaussians. It will just delete random of them, and then you need to do the whole order that you did again. And so in this early experiment, I was like, okay, I clustered them somehow. So the Gaussians that are close together in 3D and that have similar colors somehow appear together there in this grid. And then let's just apply a smoothing so that we enforce them to be close together in this grid. And then let's just train the scene and see what happens. And it kind of worked. If you can play the video, it looks a bit funky how the truck is moving around and the Gaussians are moving around. So on the left side, you see the now already trained like truck scene. If you can somehow make out the truck in the middle, possibly, and some environment of the street around it. And then I started experimenting with something called self-organizing maps. So this is like an idea from the 90s or maybe 80s even, that you can imagine like this kind of maybe fishing net on in the middle window there. So if you have this kind of fishing net where all the knots are connected, they have a neighbor to the left and to the right and to the top and to the bottom. And this is something you can always flatten. You can put it on your table and flatten it out, but you can also crumple it up into a ball. And so this is kind of, if the like strings between the knots are stretching, you can put that in 3D and crumple it up. And the fun thing about this, it's like a learning algorithm that can try to learn any kind of data distribution. So these knots here are trying to learn this 3D Gaussian scene, or this point cloud in this case. So they try to move there where the where the points are in the scene, so the track points, the color points, and they drag their neighbors with them. So it's a very simple algorithm that just, I will try to move to the next point in 3D, but also I have these connections. I have these stretching connections, the top, bottom, red, left to right, and I will drag them a bit with me. And this very simple algorithm leads to this kind of approach where you have this self-organizing map, like with its spiderweb filling the kind of 3D space. And on the right, you see like the net flattened out. So it's this kind of grid, right, with the neighbors. You have, again, the colors and the coordinates, and you get this kind of smooth results. And that's exactly what we wanted to have. So that's nice.
Okay, so this is basically what you did first. So this was the first experiment, one of the first experiments to get something running, right? And what is the problem with this approach now?
You can see it's only like 16 by 16 of these nodes, but we have like 1 million Gaussians. And so this doesn't really scale immediately. So what I did next, if you have the video maybe as well, is to say, okay, let's try a hierarchical approach. So we have learned the 16 by 16 nodes, and now every single one of them will again be one of those fishing nets, but in a like self-organizing map, but in a higher resolution. So for each of the grid cells that we organized here, let's have another one that is a smaller one. And so this is kind of the same algorithm going on, but now it's doing this for different parts of the scene and only tiny parts of the scene. So you can see these kind of networks. Some of them are maybe doing part of the truck. Some of them are maybe doing part of the street, and then trying to adapt to this part of the scene. And this was kind of working, and what you would end up with was these like maybe 256 different kind of fishing nets that were covering different parts of the scene. And then on the right, you see their like coordinates and colors, and they were very smooth.
But this is not anymore self-organizing maps. It's an extension, right?
Like now it's like a hierarchical self-organizing map, but it's still kind of a self-organizing map.
Okay.
Yeah. And that works. And maybe you have developed already an intuition why that is compressible then. So what the whole point of the compression then is to encode these grids, these colors and coordinates and so on as these images. So we don't need to deal with 3D data anymore. We can just compress these as images. And why is that helpful with these self-organizing maps? Why to go through all the trouble? Is that in image compression or in compression generally, what you want is like a really smooth function. You want like noisy data is impossible to compress, but like smooth data, you can like think, okay, what's the next data after this one? And if you have a smooth function, that's really well compressible, like your JPEG, for example, will be really small. And so with these experiments, I kind of demonstrated this idea. We can have the Gaussian scene and we have it in these smooth kind of grids, and it was working well, but it was unfortunately super slow. And I kind of ran into a wall that these self-organizing maps are really made. You have fewer knots than you have data points.
Okay.
So you will always have maybe only 1,000, or people were using maybe 5,000 or so of these nodes of the self-organizing maps, and people never did this for like 1 million. But I wanted to represent all the 3D Gaussian splats at once, right? And there are maybe 1 million Gaussian splats in your scene. And so I was kind of stuck there. I tried to approach this with this hierarchical self-organizing map where you have the like layers of them and they're detailed, but that was much too slow. And I went to my advisor, Peter, And he was like, oh yeah, there's a guy in Berlin, a professor who's working on this kind of project. I will ask him about that. And they are working in their group on organizing large data sets of images. So you have 1 million images and you want to pick one where you see a red car in them. How do you show that to people so that can find the correct car image? And they organize it in a way that you have all the images with cars and all the images that are kind of red in the same place. And they were also using self-organizing maps some time ago, but had these kind of same problems, and now had developed an algorithm called LAS, linear assignment sorting. And I looked at that, and this was kind of what I was looking for, because it didn't have the problem that we had fewer nodes than the Gaussians. So it's a different way of looking at the same problem. In the sorting, I want to sort data. How to put that? So in the self-organizing maps, right, we were looking at this fishing net and trying to move that through our scene. And now we're saying, okay, actually we already have all our elements. We want to reorganize them in a certain way. And how do we want to reorganize them? So that their neighbors are close together. And so they're grid neighbors in 2D. So my top neighbor, my bottom neighbor, my left neighbor, and my right neighbor. If I look at all the 59 attributes, so their color, their coordinates, and so on, they are all close together, still in the Gaussian splitting scene. And so the problem was rephrased from taking a self-organizing map to developing this kind of sorting. So you would just throw all the Gaussians into your 2D grid. They would be in a random order, and then apply an algorithm that would sort them effectively.
How does this work in general? Because you could imagine that you have, so it's kind of clear if you have Gaussians which are close to each other, they will have like the same color, right? So they will be very similar, but maybe they don't have the same scaling. So is this something which will destroy the order, or like put the points far apart? Because then you have like, maybe all layers are quite similar, but then you have like one layer where the points are not really close together.
Yeah, that's a really good point. And I think there's multiple answers to that question. So for one, I think Gaussians that are in the same place and have similar color should share a lot of the other attributes. So if you are like on the, I don't know, a tire of the truck, your Gaussian has this position and it's black, it probably should also have a similar scale, and it should also have like the same rotation. And maybe also have a similar like spherical harmonics already. It's like view-dependent color. But if you look at Gaussian splitting scenes from the original Gaussian splitting paper, the orientation of all the Gaussians is super messed up. If you zoom really closely into that, they are not really on the surface of anything. They're just like noisy little, like a Milky Way kind of cloud of pixels that's all together in different weird orientations. And just if you zoom out, it kind of looks like a surface, but if you zoom in, it's completely messed up. And we're saying, okay, actually that shouldn't be that way. And Gaussians that are close together in position and in color should also share these other attributes. So that should even out, kind of. Does that make sense to you?
It does, yeah. So, but this is something you are also kind of solving in the paper, because you could have, let's say you have like a white wall, and this is represented by two large Gaussians, and you have something very close by the wall, and this is represented by very small Gaussians. So they are spatial, very close, but then you have some Gaussians which blow up the sorting.
Yeah, I think, usually that never happens, that you have like a huge Gaussian on the wall, except for maybe methods that actually try to have that, but yeah, it's always like many tiny ones together, and they try to have tiny ones all together. And so it's interesting that you would expect. So maybe something else to say. So we do the sorting of the Gaussians, and then also we apply a smoothing. So we say, okay, we have sorted them some way, but then we continue the training, and continuing the training will kind of mess up our sorting a little bit, because it will drag like maybe one Gaussian away from the wall where it was previously in the wall, and so our sorting is now messed up. And so we apply smoothing unstraight. We say, okay, we want our grid that we had nicely sorted, we want to keep it smooth as well. So this does mess up some of the 3D Gaussians as well. If you can show the experiment for a video, it's not really with the current method, but it still shows how this kind of 3D Gaussian like rendering behaves if you have a large smoothing constraint. You can see that your world looks a bit cloudy, and some of the details are kind of smoothened out by you organizing these Gaussians in a way that are nice to compress. And so this is a trade-off that you do, right? You smoothen your functions to make it well compressible, but then you still want your details to appear in the final rendered scene.
Okay, but this is something we will come later to it. But you're able to solve it somehow, because finally the rendering is on par with 3D.js or even a little bit better. So there's a solution to it, right?
Mm-hmm. Yeah, it's it's a trade-off. So what's interesting in this kind of context is maybe to say working on this compression is really, I think, weird and a bit different than compressing any kind of other data. If you think about compressing a 2D image, then or a sound file, you want to have pretty much exactly the same thing that you gave it, and have it put out the same like 2D image, pixel for pixel. Here, what we are compressing is the 3D scene, but what we actually care about is the 2D renders of the 3D scene. So I don't care that you put Gaussian number 23 on the tire and Gaussian number 24 on the windshield. I just care about the rendered results. And for compressing, this gives us a freedom to both rearrange the Gaussians any way we like, but also to smoothen out these functions and to, for example, have these Gaussians in different orientations than they were maybe in the original Gaussian splitting, but maybe in a kind of better way where they are organized on a smoother surface. And this to me is a fascinating part of the Gaussian splitting compression, that you're talking about compressing a scene, but you only care about the renders. It messes a bit with your head sometimes, but I think it really sets itself apart from traditional maybe image compression or audio compression.
And so then let's kind of talk about the introduction of PLAS, or parallel linear assignment sorting, and kind of what that enables.
I was saying earlier that we had this kind of breakthrough. Okay, we actually don't need the self-organizing maps. We want to actually sort our stuff, or to be specific, so linear assignment sorting. We want to find places for individual elements in this kind of grid. And so the group of the people doing the image sorting, you remember, they had just written a paper on doing fast linear assignment sorting, and they were like, okay, we can sort up to 10,000 images at the same time. And I was like, oh damn, that's not good enough. We need to do more of them.
Just a little bit more.
Just a little bit more. And unfortunately, these linear assignment sorting algorithms, they scale with like complexity of n cubed or n to the power of 4. So if you do that for 1 million or 10 million Gaussians, you would wait till the heat death of the universe. And so they are really no good. But in the fast linear assignment sorting, they had this kind of idea. Okay, let's split up our problem. Let's not sort them all together. That is too much of an ask to find the perfect position for each and every element at the same time. Let's just pick around 100 elements out of our large heap, and let's find the perfect spots for these 100 elements at a time. And then we iterate doing that over and over again. And the idea is you have your elements. So this grid is the one on the right. So these are all the pixels by Van Gogh's Starry Night. And on the left, you have a kind of target image. And the idea is, my target is I want a really smooth grid. So I want to reorganize them in a way that they are really smooth. So I will take the grid I currently have, that's the one on the right, and I smoothen it out. It's a bit hard to see the difference, but just apply a Gaussian blur or like a normal blur function on it and have it a little bit more blurred. And then I pick my 100 candidate elements, and I think, okay, how can I rearrange them in a way that the distance to the blurred version becomes smaller. So in a way, how can I rearrange the elements in my image so that the whole image becomes smoother? And if you see the image looping in the beginning, it happens quickly. A lot happens very quickly. And then the changes are much subtler. But you can see how the elements are arranged in a way that we get this kind of smooth grid in the end. Okay, and this was working for them on the CPU with these 10,000 elements. And we were like, okay, we have to do this for a much larger problem. And so, okay, but we have already a GPU, right? For the rendering, we need the GPU anyhow. And GPUs are really good at parallel processing. So let's, and like embarrassingly parallel problems, let's throw the GPU at this. And so let's make the problems smaller by only picking 4 candidates at a time. But let's split up the whole image in like groups of 4 candidates at a time. So the whole image is like shuffled, or let's say the indices of the images are shuffled. So we have like 4 candidates that might be like one in the top left and one in the top right and 2 others somewhere else. And one of the many thousand processors on the GPU is looking at those 4 and determine, oh, should I shuffle them around to make the image nicer, or should I keep them the way it is? And we do that for all the elements at the same time. And we do that thousands of times. And so we are able to sort these kind of really, really large heaps of data in a time that does not take the whole universe in a time.
Does it also work if you take like nearby candidates? Because intuitively, if you smooth the image and you have like a target, smooth point should be close by, right? And now you're taking like random points.
Yeah.
And this is more effective in sorting. Did you compare it, or does the local sorting have a problem?
No, it's actually a very good idea to do it that way. And so you see that there's a progress in this video where first it's like a global sort, and actually we were able to have the candidates pick global candidates from everywhere. And then we reduce both this blur filter, so we don't blur as much anymore, and we also reduce the radius of like candidates. So we will look only in a smaller area for stuff to change out. And so exactly. So this is also, so the whole process also gets much speedier towards the end of it. The first step is really, really slow too, because you move around a lot of the elements, and then towards the end, all the iterations speed up a lot because you don't have to move as much anymore, and you don't have to look as far away to move them.
And so with the scope, needing to sort potentially millions of Gaussians, you're still able to achieve this in a very fast way. Like this isn't something that's even going to take like minutes or really increase the amount of time that would take to train a normal Gaussian splatting file, for instance, right?
So we measured for the truck scene that one sorting took around 10 seconds on a RTX 4090 GPU. This is the fastest we got at that point. And this is plenty fast to do the sorting, but it's not fast enough to do that at every iteration of the Gaussian splitting training, because you do 30,000 iterations, and you doing the sorting every time wouldn't work. You would have to wait for too long.
And that truck scene is like 2.5 million Gaussians?
Yeah, you're right. So it's 2.5 million Gaussians in the original Gaussian splitting, and so we were like, okay, we have to reduce the number of sortings that we do. We can't do it every iteration. But then we were discussing earlier how the Gaussian splitting works by adding and removing Gaussians from the scene by running the densification all the time. And every time you do that, you have to redo the sorting, because now you messed up your sort. And so we don't want to do that every 100 steps. Actually, let's just do that every 1,000 steps. So that's quick enough to do the training. And so we had to shuffle around the parameters of the Gaussian splitting training a bit, and we have to do this densification not as much as in the original paper. And then we had to adjust some other parameters, because now we were getting not enough Gaussians anymore. And when we had done that to build in our sorting thing, actually we ended up with fewer Gaussians in the scene than the original paper did. And so our scene actually trained pretty much the same time as it did before. So we took the same time to train. So we were slower because we had to do the sorting, but we were faster in the end because there were fewer Gaussians to train. And so this funnily evened out to nearly exactly the same second of training, like 15 minutes and 3 seconds and 15 minutes and 5 seconds or something. So there's an overhead from the sorting, but it evens out with the number of Gaussians you have.
Okay, and because you then sort less, you are faster in sorting, right? And you have less Gaussians, you are training faster, so you're optimizing faster. Okay,
you've also been getting the same reconstruction fidelity, though, even with significantly reducing this. It's not like you're trading off the visual fidelity, right? As part of this.
Yeah. So that was something that surprised us, that even though we were using fewer Gaussians and were smoothing away some of the values, we got the same quality and sometimes even higher quality than the original Gaussian splitting. And I think that, for one, it shows that there is some kind of optimization that you can do with the parameters. And on the other hand, I think it shows you that this smoothing can be kind of good to, natural surfaces are usually also smooth functions. And actually it does, I think, help it sometimes to, for example, get rid of floating artifacts. You have tiny little floaters that may have appeared in the original 3GS that now in our scene are kind of moved away because they couldn't be sorted in anywhere. And I think this actually helps with the quality sometimes.
So tells us people should compress their scenes, right, and not keep them large. But fundamentally, you have noticed attributes all sorted, right? 59 grids of attributes. And now what? What is the next step?
So we have 59 images essentially. So this is the only thing to do is somehow store these images on the disk. So you can just use JPEG. So we've been using, for example, for the color, we've been using JPEG XL to encode these images, and that compresses really, really nicely to files because we have these smooth functions. There's some quantization involved. So your Gaussian splits, they have 32-bit float values, and you don't actually, for most of the values, don't actually need that large number of different values to encode. We quantize them to sometimes 5 or 6 bits, so only 64 different values. It's very similar to what people do with code books and other kind of compressions. The colors can be really nicely encoded as images. The positions, so the coordinates, the XYZs, they need a lot of data actually. They are like the biggest ones, because you will really see if you only have like 255 steps that you allow, and your scene will get really messed up and will look like really holy. So you need the most kind of bits for that. And also we introduced a log activation, saying, okay, actually we want to have most of the values encode the stuff in the center of the scene, and the stuff that's further away we don't care so much about the precision of that. It's a bit similar to what they did in the MrNeRF 360 paper, and that also have this kind of log activation of the coordinates. And that also helped, and that also may be useful for the kind of quality that we saw for some of the scenes where actually the like power of the model is concentrated to the center of the scene.
So finally, you're storing images, right? So you have like 59 images, which are compressed by JPEG, and you store them as images.
Yeah,
cool. Yeah.
And you can do this with any of these like off the shelf. At this point, in the process, you're able to take any off the shelf like imaging compression method to at least see how it functions or affects the reconstruction, right?
Yeah. So as I said, you need weird like numbers of bits for example, the coordinates, and so your JPEG has only like 8 bits, and so you need something like JPEG XL that can do more bits. But you could I did experiments with PNG and JPEG and JPEG XL and something called EXR. So all these kind of image codings fundamentally just work with it.
Mm-hmm. And now so you have this compression now, and you can apply it with the training process. But if, let's say, I have a PLY file, which I import from a different training, I couldn't just compress it, right? Because it's not trained with all the bells and whistles you're applying, the smoothness, and so on. So in the end, it's not compressible in the set, or not in the same. The compression wouldn't be as strong as your, right? Because then you have different parameters, and they are like, you don't have the closed Gaussians by each other, and you have different scales and so on. So it wouldn't work the same way. It's basically not possible to achieve the same result with an imported PLY, right?
Yeah, that's what we argued in the paper, and it goes a bit together with what I've been saying earlier, that this kind of compression of the 3D scene is a different one, and the kind of mistakes we do by smoothing out the Gaussians, we can then fix by training and putting the Gaussians back to where they should be. And we did some ablations in the paper where we showed that actually during training is very important. But then somebody came along and implemented our method on top of G-Split, the Nerfstudio people, right, who have G-Split. And they were using a different method of initializing and placing the Gaussians with this Markov chain Monte Carlo Gaussian splatting. And they just applied the sorting after training, because they didn't want to do it during training, and they just said, okay, let's do it just after, and then just compress this stuff as PNGs. And amazingly, it worked super well for them. It's one of the leading like compression formats doing it that way. And so if you have a really good Gaussian splitting scene that maybe is already very naturally placed the Gaussians, and also maybe has solved the kind of surface problem and the weird orientation, then actually you can just do the sorting after the training and don't have to do it during training at all.
And so can we talk about some of the actual like quantifiable results here? Because it's pretty shocking, the amount of compression rates that you're able to get by implementing your method. Mm-hmm. I'd love to talk about that.
So it's interesting that, so maybe it's also fun to talk about what can you do to compress Gaussians. The easiest thing, you can just throw away stuff. So we were talking about how the original parameters weren't that great, and they created like 2.5 million Gaussians, and that's not actually needed. And by just throwing away, you already saved half. and then you can do some quantization, and instead of using 32 bits, you maybe only use 5 bits, and so you have another factor of 6. So you have a factor of 2 and then a factor of 6, and then you do the log activation, and then you do the organization of your Gaussians, and then you have another factor of something, and you end up from the original track that was 650 megabytes. You end up with our method somewhere, I think 20 megabytes, I've looked so often at the teaser image, 22 megabytes or something. So it's a factor, we saw something between 15x and 40x. So it's crazy numbers. So these PLY files are really not that great to share. And there's lots of headroom to do the compression. Yeah.
So I think you are aware of the blog, and you're also citing in a paper, Ara's blog, who was the first one applying compression. And he also got the PLY files really small. So how does it compare to your approach?
So yeah, by now there's lots of different methods out there that do compression of Gaussian splits, and the blog file. He was working on doing 3D to 2D mapping as well. So it's a very similar idea, actually. But while we doing this kind of learned stuff where we have these self-organizing maps or self-sorting maps, he was using Z-curves or Morton order curves, where you have this predefined function that says, okay, I have a function that goes in a spiral around in my 3D space and maps in a defined way somewhere else. And then I can use this to store this and as a quantized PNG. And this is works also well. But so what you get with this kind of Z-curve is you will get the neighbors are close together, but the next time you come around with a spiral, the function might end up somewhere completely else, and the neighbor you get there isn't really close to that. And so these predefined functions, they kind of do the job somewhat well, but you leave some of this self-organizing that really gets you over the final bump for the compression. Yeah.
And so one of the other learnings too that I thought was really fascinating was that when you were taking a look at removing or sorting by opacity values as well, you're able to get a shockingly high amount of those removed before you start to see any visible reduction in rendering quality or reconstruction quality.
Yeah. Absolutely, 30% of them you can just throw away and you won't even notice.
Yeah.
So I think it shows us that there's a lot of stuff at the time it was very low-hanging fruit. By now, I think people have worked on this kind of thing, but there's papers maybe mini splatting or AtomGS and papers like that look at how can we actually represent our scene with using much fewer Gaussians. And for example, if you can just throw away a third of them without seeing a difference, that shows you there's a lot to be done.
And so when we look towards the future and ways that you could continue to improve, I think one of the ways that you highlighted this could be is to perform the actual quantization during training itself. What's kind of that direction looking like, or what are some of the other potential improvements for the future?
Yeah, that's a good one. So for now, we just do the quantization after the training and just apply it, and then we lose some of the details. And that's not a good idea. So you would want to do that during training so that you can restore some of the details and actually have the Gaussians move to places where that's good. That's one of the things you can do. And also, generally pick together different ideas from different places, like this MCMC initialization or quantization-aware training, and maybe you can also do something that makes the grids really nice to compress for JPEG or something. I think there's great ideas to combine from other papers, from minifying papers. If you have fewer Gaussians, then you don't need to compress as much, so you get much smaller scenes. So I think there's a lot to do to combine these ideas. Unfortunately, in the research world, it's really hard to get this kind of thing done. So you do a small improvement on something by combining two ideas. That's not really such a great paper. And so unfortunately in the real world, I would really love to really perfect this kind of compression method. But it's tricky to do that because what are you paid for it? And how much time can you spend on really providing this kind of open source compression implementation that takes together different approaches?
What do you think? I mean, in an ideal world, where compression will take us. So, do you see what impact will it have on Gaussian splatting? So, let's talk maybe about dynamic Gaussians or mobile.
Yeah, I think that's a good motivation to do compression, right? So I can stream it to my phone. And so the static scenes are small enough that I can have that immediately on my phone. And then also it's exciting to me, like hopefully we can get the compression good enough that you can have a whole city, right, on your machine. I mean, how awesome would it be to have like the whole globe in Gaussian splats accessible to you in a machine in a flight simulator, or maybe even to use for research in like climate modeling or stuff.
Yep.
So if we get the compression good enough, I hope we can get there. And also, dynamic Gaussians are of course another dimension where if you have something every 30th of a second, that adds up really quickly. And I think our method with image compression also lends itself rather well to do the kind of dynamic stuff, because then you get a set of images, right? That you can compress that well. So that's something I'm interested in.
Yeah, it's pretty incredible to see like the potential scope of which these representations can reconstruct, because I do know there are people who are pursuing city-wide reconstruction and larger. And for those actual models, when you get to that size, the more compression, the better, and the more transferable it becomes. So I'm very excited to see how this actually naturally progresses too.
It also goes together with like rescaling the scenes, like this kind of level of detail stuff. So I have the city and I'm looking at it. I don't want to have the full detail of all the billion Gaussians. I want like a smaller version scale that I can render now. And if I get closer to it, I want a higher detailed one. So this is something that has been existing in video games for a long time, right? To render these kind of large worlds. And also this is something I'm excited to work on with the like grid-based Gaussian splats, because it's an image, so maybe you can scale that down and up somehow and use this for this kind of level of detail stuff. That would be amazing if we can work that out somehow.
And I think when you were first publishing the paper, I think the largest one that you trained on was about like 4.4 million Gaussians, and then I know I've also trained some pretty large ones within like the Nerfstudio environment. But is there like a fidelity or a upper level cap right now that you've identified since then? Or is it something that, if there were a billion splats, that it'd still be able to handle?
So, I've been talking about this same thing. Like people came up to me at ECZV and were like, okay, I have this robot running around and it needs like 20 million Gaussians. Can you handle that? This kind of stuff. Currently, the bottleneck would be the sorting. So we did some ablations how well the sorting scales, and I think we can sort up to like 16 million, and then it gets so slow that you can't be bothered to do that anymore. And so this is something that we're currently working on. We have some ideas to make that a lot faster, so that we can then hopefully soon scale to much, much larger scenes.
Right, because I think that was something you identified in the paper, is that you would imagine as the training iterations increase that they would get more and more progressively more organized. But that's actually like not the case, right? They actually get, because these lists become so large and so complicated, there's not that straight one-to-one. More steps equals more organization.
Yeah, maybe there's something to do there with also splitting up your scene into like different parts and doing that individually. And this kind of goes together with like original idea of these kind of small hierarchical self-organizing maps. Maybe something can be done there. as well. But yeah, if you do the initial sort of your 1 billion Gaussians, it's a really hard problem.
Is there anything else that you want to kind of highlight or share with the listeners right now in terms of your work or anything else?
Maybe one thing I think that doesn't get talked about enough is complexity of stuff. So I think one thing I really like about 3D Gaussian splatting, and I think that really led to its success, is it's super simple. Everybody can read a PLY file. Everybody can write a PLY file, and the rendering is so simple that people have started writing their own renderers. And so I think simple beats complex. And I also think the explicit modeling beats implicit. So right with NeRFs and instant NGPs, we have the problems. We can't really edit them. We don't really understand what they do. With Gaussian splats, we actually can select them in 3D and remove them or blow them up or change their color. And so this kind of explicit stuff is really interesting. And so I'm kind of excited for our method as well, because I like the simplicity of the coding scheme. So it's just a bunch of images and you decode it and you get out your Gaussians. And I like these kind of methods that are, once you've understood them, are like just a one sentence explanation of what they do. And for the future, I would kind of hope that the compression community of Gaussian splatting compression settles on maybe one method that we can find and support everywhere. We don't split up too much, and combine these kind of ideas that people are having from the sampling and from the throwing away Gaussians and from the quantization and from the coding together to form something. So I'm hoping the community there comes together and builds something. So all the stuff we do, we always put on GitHub and try to support really well. And so I'm asking anybody to try out our code, and if they're experimenting with that, we are happy to support that and hear your feedback on that as well.
So along those lines then too, if you are a listener, where can people either find your work or follow along as you continue to release more publications and research?
Yeah, you can Google my name and find me on Twitter and LinkedIn, of course. But then it's just great I think the most exciting stuff happens on GitHub for the research part, so I can follow up there and see what we have cooking there.
Cool. This was super interesting. Thank you very much for the discussion and also teaching us a little bit about the compression approach you invented. It's very remarkable how small you get the files. I learned a lot today, so it was a lot of fun to have you here with us. Thank you very much.
Thanks for having me. It was a lot of fun also to talk about it.
Cool. Well, thanks so much again, everyone, for tuning in, and we will return next week with yet another episode of the View Dependent podcast. So thank you so much for everyone for listening.